Hi students, welcome to Physics for Everyone classes. This is your Satish sir. I wish everyone a happy Independence Day. In this video, I am discussing the Lenz law. In the last video, we have seen the two Faraday's laws that we completed whenever there is a change in flux linked with the coil. An induced current or induced EMF is developed in the coil. And the Lenz law is the extension of the Faraday's laws. We can say the Faraday third law to know about the direction of the induced current. Here we have the statement for the Lenz law. Let us see once. The direction of induced current is such that it opposes the cause that produces it. To understand this statement or to find the direction of the induced current, I can explain these things with the help of the diagram. Let us see. Here I am taking a circular coil. As usual, the plane of the coil is perpendicular to plane of the board. Here, on the axial line, here is the axial line of the circular coil. So on this axial line, consider a bar magnet. Here is the bar magnet. The two things are important. So which pole is closer to the face of the coil? North pole. The north pole is moving towards the coil, which means that the magnetic flux linked with the coil gradually increases. You can see the magnetic lines of force are starting from north pole, passing through the area of the coil, and these lines will end at the south pole in this manner. So what we can see, if this magnet is at rest with respect to this coil, which means if there is no relative motion between these two, no induced current is developed. Now we are doing, this magnet is taking towards the coil. Consider a person who is sitting on the magnet and he is observing the face of the coil. You can say this is the left face of the coil, the other side is the right face of the coil. We are just looking only the one face, which is the left face of the coil. Who is saying this one? The person who is sitting on the magnet. Now he is saying the magnet is moving towards the coil, and also the flux which is passed through this coil gradually increases, or the field lines are moving from left side to right side through this coil. Suddenly an induced current is set in this coil. In this condition, when it is moving towards the coil with some constant speed v, there is an induced current is developed in the coil. We need the direction of it, and we are taking the help of the Lenz law. The direction of induced current is such that opposes the cause that produces it. The induced current is because of this external flux. I name it as this is called as the phi E, which is called as the external flux. If the external flux is changing, then only induced current is developed in the coil. Once the current is set, that current carrying conductor also produces magnetic flux or magnetic field, and that induced magnetic flux should oppose this increasing flux. This is possible only when we consider the current in this coil is the anti-clockwise direction. You see here, if suppose the current is set in the anti-clockwise direction, as you are studying magnetic effects of electrical current, every current carrying conductor produces a magnetic field around it. If it is a circular current carrying conductor, the field lines, the magnetic field lines, the direction of the magnetic field is given by the right hand thumb rule. As you know, suppose the current is moving in this direction. For me, it is anti-clockwise direction. For you, it is clockwise direction. The thumb is giving the direction for the magnetic field. If, with respect to me, if the current is going in the anti-clockwise direction, the magnetic field is towards the pole. The same thing, if you apply here, the current is moving in the anti-clockwise direction with respect to this person. This is the reason why I am taking the person on the magnet. So this is very important that to judge the direction of induced current in the coil, we need a reference. If you change the position of the reference, the direction of the induced current might change. Suppose the same person, if he is standing the right face of the coil, for him the direction appears as clockwise direction. So be careful of from where we are taking the observations. So with respect to this person, the current, induced current set in the coil is in the anti-clockwise direction. So if you take like this is the coil, here is the coil. The current is moving in the anti-clockwise direction. The thumb is towards left direction on the board. So we need to draw a few magnetic lines of force towards left direction. So this flux is called as the induced flux. This flux is opposite to the external flux. Now I am drawing the induced flux. And these are the lines. And it is named as phi I. See clearly, this induced flux, which is opposite to the external flux, means opposition. The induced current which is set in the coil in such a way that the flux due to this current named as induced flux always opposing the external flux. So in this way, we can find the direction of induced current in the coil depending on whether the external flux is increasing or decreasing. Here in this case, the flux is increasing because the magnet is taking towards the coil. Now tell me, if this circular coil acts as the magnet, then it contains two polarities. One is north pole and second one is the south pole. So bar magnet, we have conventionally taken one side is north and another side is south. But for the coil, how we can judge one is north pole and second one is the south pole? As the field lines are starting from the left face, that face comes as the north pole and the second face comes as the south pole. So the left face is named as north side and the right face obviously comes as it as the south side. We can see when this magnet is taking away from the coil, here the same magnet which is taking away from the coil with constant speed. Now the magnetic lines of force which are starting from north pole are still passing from the left face of the coil to the right face of the coil. Like this they are moving. But only the difference is that as this magnet is moving away, these field lines are gradually decreasing. The flux linked with the coil is decreasing. With this, an induced current is developed in this coil. We need that direction. Now, this external flux, which is passing through the coil, is gradually decreasing. Now, according to this law, the induced current which is set in the coil creates induced flux that should oppose the external flux. Now be careful. Here flux phi A is decreasing. So what you can say, the opposition to decreasing is increasing, which means that the induced flux which is developed in the coil should be along the direction of the external flux, then only we can say there is an opposition. So means the right face of the coil becomes as north pole, and the left face of the coil, if it comes as south pole, then the condition will satisfy. You can see here, I'm taking the right face as north pole, which means from the other side, the field lines are being started in this manner. Which means on the right side, the field lines are starting. On the left side, the field lines are entering into the face in this way. They are entering. Now this current carrying coil is behaving like a magnet. The left face comes as a south pole, whereas right face comes as a north pole. And this flux, which is called as induced flux, this is opposing the external flux, which means as phi is decreasing, this flux is supporting it. It is as simple as that. You see, somebody is growing. Generally, the human tendency is that we cannot support him. We are seen in the earlier case. If somebody is below compared to us, then certainly when we are tending to help that person. Here is the case. This phi is decreasing. This is the reason the induced flux created in the coil is opposing, but here it appears as supporting. This is possible when the current which is set in the coil is in the clockwise direction. You can take the current which is the clockwise direction. You can see here, if the current is in the clockwise direction, the thumb which is towards the right side, the magnetic lines of force which are emanating from the right face is towards right. So this face comes as north pole and left face comes as south pole. So if we ask the question, what is the direction of induced current here? With respect to the person on the magnet, because he is looking this observation and this person is giving the answer, the induced current direction is clockwise. That is right. Don't say the induced current is anti-clockwise, because if you see from that side, the answer comes as anti-clockwise direction, because there no person is there to observe. We are taking the person on the left side only. This person is always looking only the left face, and he is saying the face of the coil is south pole and the direction of the current is the clockwise. So what is the face of the coil? For him, south pole. For him, the direction of the induced current is clockwise. Don't give the answer, the face of the coil is north pole. If somebody else is standing there, if no person is here, then you can take the answer as the face of the coil is north pole and the direction is the anti-clockwise direction. But we are taking in the two cases, the person who is on the bar magnet side. This is most important, on which side the observation is taking place. So in this way, we can find the direction of induced current, whether the magnet is moving towards or away from the coil, with its north pole is facing the coil. The same scenario will be applied when the south pole of the bar magnet is nearer to the coil, whether it is coming or moving away. So I'm giving a work to you to find the direction of induced current by reversing this magnet, which means the south pole is facing the coil, whether it is moving towards the coil and also away from the coil.